time. So not just the meaning, but also how it's organized in space and time. So what are the principles for at work, in particular in the dialogue? So you see here two famous logicians, Abelard and Eloise, interacting together. What's happening when they discuss together? And so the purpose of this talk is to understand how different proofs programs may be combined together in space and in time. And to that purpose, I will work with game semantics, and we will see at some point linear logic and even differential linear logic coming in. And so the question is, how does logic, in a way, and really this is the whole purpose of the talk, how logic and its algebra defines a specific kind of dialogue. And so I will start with linear logic seen from, through the lens of game semantics. So the idea is that every proof of a formula A initiates a dialogue where proponent tries to convince opponent and opponent tries to refute proponent. Okay, and so in this way, this is an interactive understanding of logic and programming languages. And so a typical example is this formal proof of the drinker's formula. Okay, and so in this proof, there is, let's say, clearly it's a proof in some formal system, but the question is what happens from the point of view, from an interactive point of view. And so it's called the drinker's formula because, so maybe I can try to share, wait a minute, sorry, to share with a pen. So I will try to do that. Yes. So, sorry for that. Yes. Yes. So, just for the, because there is no board really, so maybe I thought I could do that. Sorry. So we go back to where we are. Yes. So really, we have this formula here, and this formula is very nice because it's provable in classical logic, but it's not provable in constructive logic, in intuitionistic logic. And so this is the formula. And so what it says is that if you call A of X, X is drinking, so you enter in a pub or in a bar and you want to know who is drinking, and so the formula says that there is a customer who is so sober, and this is the customer Y, that if he or she is drinking, then all the other customers are drinking too. And this is very this is kind of counterintuitive, okay? But still it's true in classical logic, and this is the proof, okay? And the proof is very, very small, okay? It's not a big proof. And then the question is, what does it mean from a dialogical point of view? And that's the way the formula is proved. Okay, so imagine I try to prove you the formula. So I enter into the pub with you, and then I find a witness, any witness. Okay, so I say, I don't know, maybe Ulrich, do you agree to be the first witness? So I say, this is Ulrich. Yes.
Okay. Yeah. Sure.
Okay, so this is Ulrich is the Y. Okay, and then, well, you disagree with me because you are my opponent. and you say, come on, no, I mean, Ulrich, you know, is very sober. He's not drinking now, as far as I can see. But then Harley, okay, maybe he's drinking. Sorry, so Ulrich is very, yes, but Harley, he is a counterexample because he's drinking, yes. And so then the prover, so okay, if I want to convince you that the formula is true, I will say, okay, sorry, I completely, thank you, Harley. Sorry, I completely, I mean, it's terrible, I made a mistake. You're right, okay? The appropriate witness is not Ulrich. I should have picked Harley at the beginning, okay? And then because Harley was drinking, then the formula is true, okay? And so the point is that, sorry, yes, I hope I didn't, yes. So the thing is that the fact that we were able to prove the formula comes from the fact that, in fact, during the, so if we look at the proof, we can see the interaction. So the first here exists is, you know, the player picks a weakness. Okay, so player pretends to know the weakness, but then opponent here finds a counter example. Okay. And then so this is here the opponent. And this is why this is a for all here, okay? Because this is like an existential, but for the opponent. And then the player here, okay, changes, the player changes the witness, okay? So it picks the witness of the other, of the opponent. And so really the reason why it's not constructive is that the player needs the information from the opponent in order to convince the opponent and get the property right. Okay, and the fact that if we look at it from an algebraic point of view, the fact that here we were able, so the player was able to pick here and here the witness twice, here and there, okay? And so has to do with the fact that we were able here to duplicate the formula. So this is the famous contraction rule. And so you see there is this very nice connection between the algebra of proofs, the fact that we were able to contract, which means to duplicate a formula. If we look at it from that, in that direction, in the direction of proof search, we had one formula, suddenly it becomes two formulas. And then the fact that we can play the two existentials. Okay. And so if we look at it, the intuition I gave at the beginning of, you know, a player cheating in a way, because, you know, I start by picking a witness, then you give me another witness, and I pick your witness, is much easier to understand from a you know, very direct, intuitive point of view than this you know, pictures. Yes, so this picture, yes, this proves. And of course, so I like to think of these proofs as some kind of formal notation, like in music. And then game semantics is more like the music itself. So it's the meaning that is conveyed by the proof. And so that's why I'm interested in the algebra of proofs with respect to the game semantics. And so maybe we can carry on like this. So the fundamental aspect of game semantics is the idea that there is a duality between the player and the opponent. Okay, so so if player plays the formula A, the opponent here plays the formula negation of A. Okay, so negation permutes the roles of proponent and opponent. And so here, okay, you have the white playing, and in the game not A, well, really the white becomes the black. Okay. And so negation permutes the roles of opponent and proponent. And then there are a number of basic combinators on games. And these combinators are extremely simple, elementary, and important. So the first one is the sum. Okay, so here. So what it does is proponent, okay, will select the board which will be played, and then the game carries on. So imagine this is like, for instance, chess and poker, okay? And proponent says, okay, I want to play chess. And then only chess will be played, no poker will be played, okay? So this is the sum. But then there is, which can be seen as a kind of constructive disjunction. Okay, so the player picks the component the player wants to play. Okay. So it really is a disjunction. But there is also a conjunction, which is the dual, where opponent selects the board. So imagine this is chess here and poker. Then if opponent chooses to play chess or, to play poker, then I, as player, as proponent, I should be able to play the two games, chess and poker. So in that sense, it's a conjunction, because I don't know what the opponent will choose. I need to master the two games. And then it can be seen as a form of constructive conjunction. Then there is another pair of combinators, the tensor product, where the two games are played in parallel, and opponent is allowed to switch board, but not player. By the way, if anyone wants to ask questions during the talk, I'm happy to answer them. Yes,
yes. Hello. Hi, Paul.
Yes.
This is Paul-André. What does it mean precisely to switch the board?
So here, for instance, imagine I'm playing that game, which is the tensor game. Yes.
Yes.
And so I'm playing, like, I'm player, okay, and I move here, okay, I move that, okay. Then I'm player, okay. Yes. So the opponent will answer, but opponent here is allowed to switch board. So maybe, I don't know, opponent will play this, okay. But because I'm player, I have to play on that board. I cannot switch, okay.
You have to alternate board.
And then, yes, and then opponent. So opponent here can pick any time. So for instance, opponent can play now here. Yes.
So you have to alternate strictly. The opponent can schedule his moves any way he wants.
Yes.
But you alternate moves. The opponent doesn't get more moves than you do.
So opponent doesn't get more, but the opponent can switch from one board to the other anytime.
Okay, good.
Yeah? And here I take a very basic, and I will focus on that for the first part of the talk. I focus on a situation where opponent and player alternate. Yeah. This is the tensor product, and so clearly opponent has a little advantage, because opponent can choose to change anytime. Opponent maybe, is bothered to play somewhere, then opponent will move to the other game, other board. And so, in fact, we will see it can be seen as a form of classical conjunction. I will explain why in a minute. Okay, it's not obvious, but the difference with the previous constructors is that here the games are played in parallel. And by the way, I should mention game semantics is very much inspired by concurrency theory. So the plus we saw was really about choice. Okay, so player or opponent chooses the board, whereas here it's really parallelism. But there are two forms of parallelism. This is the beauty. There is this form of parallelism, but also the dual, where now player here is allowed to switch board, but not opponent. And so player has more power here. Okay. So let me prove.
Hey, Paul-André, I think Bruno has a question on the chat.
Yeah, sorry, I don't see the chat, so I should.
No, that's okay.
More,
Thank you.
Yes.
Hi, so I can read a question. I guess.
Yeah, please.
Yeah, I guess I just meant, is this what's called an asymmetric game in game theory stuff? Because the players don't have, I guess, the same options.
Yeah, but the situation is probably a bit different, but because yeah, you can say that there are. I mean, something nice about game semantics is to understand the connection to game theory, and in particular, as they are used in economy. But so it's like here, there are games which are repeated. Okay, so you can play several moves one after the other. But yes, so there is an asymmetry, but maybe of a different nature. It depends on the situation. But you can say there is an asymmetry here. Yes.
Right.
And this is the whole. In a way, this is the whole. Let's say beauty of logic is that it's very symmetric because we use language on both sides. But anytime or is different from and. Okay, and is or let's say or is like a conjunction is like the disjunction of the opponent. Yes, this kind of symmetries, but they are still. Yes, but so I don't want to.
Right, I see. I guess you mean in some aspect there's some symmetries between what's happening, but in other
symmetries and asymmetries. But the thing is that maybe asymmetric games are about knowledge. Yes. Anyway,
might
so
be. I'm not too clear, but yeah. All right. Thank you.
So here, there are, in these games, but there are other variants of games. Here, the players have full knowledge, yes, of the situation, in particular the current state.
So
Anyway.
sorry, just to interject a little bit.
Yeah.
So does this establish the parallel product as some kind of dual of the tensor product?
Yeah, exactly. This is exactly the idea. So yes. So yes. So sorry. And so here, this is where we get, okay? So I will prove you that not A or A, yes? In this little system, logical system of games, okay? So what this means is that I will show you how to beat. So I take the game chess. A is the game of chess. And we saw that not A is like chess, but up, yes? So it's just like chess, but seen from the other point of view. So it's okay. And so now if I take OR, so we saw that OR is really like playing in parallel, but now the player, like me, I am the player here, the proponent, is allowed to switch board. And so I will show you how to win that game. It's very simple, you will see. So the idea is that I'm playing typically against two very good players. And I let white start, maybe playing like this, yes? And so then the thing is that because I am the proponent here, I'm allowed to switch board. And so what I will do is just take the same pawn here and play exactly the same move here. Yes, you see? So this is, maybe I could, yes, I'm just repeating, yes. And so now the Karpov will just react to that move by playing blue here, yes? But then what I'm doing, because again I'm proponent, is just playing the very same move on my board, yes? Maybe I could, so here I'm supposed this, Yes? And so then Korchnoi will answer, react to that move, and I will repeat. I mean, I will just take the move that Korchnoi has played, and I will play it on the left board against Karpov, and so on. So it's called the copycat strategy. Okay, it's a very stupid strategy. So, but the thing is that in the end, if chess is determined, okay, so we suppose that chess is determined, I will obviously win on one of the two boards because Korchnoi or Karpov will win. So imagine Karpov wins. So imagine Karpov is the winner. So here, of course, I lose here, but I win here because Korchnoi believes I am Karpov. Okay, but then the winning condition for this junction is really that I win on one of the two boards. Okay, and so I win the game. Are you happy with that? Yeah. So what this shows is that the fact that I had the ability here to move from one board to the other gives me an extraordinary power, because I can implement this stupid strategy of always moving one action on one board to the other and conversely. Yep. Any question or reaction? Okay. So this is where the connection with logic suddenly becomes quite fascinating, because we see with very simple combinators, tensor, cotensor here, the parallel, the dual to the tensor, and the sum and the dual of the sum, well, we see that they express very stupid and fundamental basic principles of logic. Okay, and so the question is, what can we learn from that? And so, and it gets even more interesting when we include the exponential modality of linear logic. And the idea is that if I have a game, I can define the game bang of A. Sorry, for some reason. Ah, yes, okay. And that game is defined in this way. It's a game where opponent can open as many copies as necessary to beat proponent. So the idea is that, okay, like we start to play on that board, but at some point, opponent feels like threatened. Okay, so well, opponent will say, okay, I will open a new copy. And then maybe at some point, another copy. So the only limit is that opponent is not allowed to open an infinite number of copies. So it should be finite. So from that point of view, the modality is inductive from the point of view of opponent, but co-inductive from the point of view of player. Okay, so if I want to win as a player, I need to have a good strategy that can handle any number of new copies here. And opponent, on the other hand, can explore my strategy by opening a new copy. And that's really the idea of this modality. And so you see, yes.
Opening up new copies is kind of like using contraction a lot. Once you open up a copy, can you get rid of it? Use kind of like weakening to delete it?
Yeah. So opponent can get rid of a copy.
Okay.
Yes. Thanks.
And
also come, of course, open a new copy, but then come back to the previous one. That's the way it's okay. But maybe I should stress that this is exactly what we saw with the Drinkers formula. Okay, so in the case of the Drinkers formula, we had an existential, so opponent was, giving us a witness here. I mean, in that case, I was playing the opponent, but I open a new board at some point. And so, in fact, the Drinkers formula can be understood, and in fact, classical logic can be understood using that modality of linear logic. And this was started in the 80s by Girard and his school, people trying to understand the classical logic from the point of view of this exponential. I should mention that this was also, although it was not expressed as a modality, but that was also you know, a tradition in game semantics, trying to understand the difference between different notions of logic, you know, in the Lorentzian school, by the idea of backtracking. Can I backtrack or not? And so backtracking is really has to do with this modality here. Yes. Any question?
Yes. Okay. So on any turn, the opponent can start one game or a finite number of games.
Doesn't change. It's not a big difference.
Doesn't change.
The tradition,
Okay.
the tradition is to open one game only.
One game, but okay,
because
yeah.
it's alternating.
Finite number would not change it. So he can't spawn off an infinite number of games in any one turn. That's
the point. Even in the end, so when
Yeah.
you know the game carries on, so it produces a possibly infinite trace.
Yeah.
The opponent is not allowed to open an infinite number of copies. So from that point of view, opponent is inductive. Yes.
Okay, but he can open an arbitrary number. In other words, he can
Absolutely.
go with the natural numbers, basically.
Yeah,
Right.
but at some point it should stop. But the player, me as a player, I don't know how, you know. So it's a typical situation of like, for instance, lists versus streams. Okay. So if I want to behave properly, I should be ready to play a stream of games. But on the other hand, the opponent can play only a list of games.
Is each game finite or infinite?
It depends. It can be infinite, typically infinite. Yeah.
Typically infinite. Okay.
Yeah, because you will have nested, you know, exponential modality.
So how do you even say that at some point it will stop? Because at any given point, there's only a finite number of games open. Okay, yeah. But so are you saying that in the limit you can't have an infinite number of games?
Exactly.
Okay, fine.
In fact, I should mention the fact, I mean, it's an interesting fact that now logic in the limit is something that people spend a lot of time thinking about it. Even there are beautiful connections between linear logic, that's what I'm discussing now, and higher order automata theory. So,
right,
where,
okay.
like,
yeah,
it's very interesting field of research.
And it's a little bit reminiscent also of some results in topology which hold for finite products but not infinite ones.
Yeah. So yeah, it's of course, but this connection is something that people very early understood in the 90s, and when looking at categorical semantics and topological semantics of linear logic.
Right.
So I will come. I will come a little bit back to it. We will see. I want to carry on, but we will see a connection with the construction of the free symmetric monoidal category. So at some point I will explain how the exponential modality can be interpreted using the construction of the free symmetric monoidal category on a category, but we're not there yet. Okay, so, and there are these two beautiful isomorphisms here. I mean, so there are the isomorphisms which convince me to study linear logic. So the first one says, and they are dual. So if you understand the first one, you understand the second one. It says, okay, if opponent is allowed to open A as many times as desired, and same for B, with a tensor in the middle, and tensor means gives priority to opponent. So here, opponent is really like, you know, very happy. It can open. So maybe a drawing would be, there is, you know, a big bag of A's and a big bag of B's. Yes, right. This is the same thing as having a big bag of A with B. Okay, and the reason is that if opponent wants to open a new copy of A, okay, or a new copy of B, it's possible here, but it's also possible here because opponent will just pick a copy of A with B, and then opponent also has the ability here to choose between the copy A and B. So opponent will pick one copy of A with B, and then pick whether he or she wants to play with A or B. Yeah. And so this, so here, this is called, tensor is called multiplicative. So, and here it's called additive. And yes, I wrote it. And the reason is that this is reminiscent of this isomorphism. You know, the power set of A times power set of B is the same as power set of A plus B. But here now, the novelty is that we have a notion of opponent versus proponent. Okay, so it's really like some kind of duality appearing, which I would say is the essence of logic. Okay, this duality between someone who wants to prove, someone who wants to refute. Okay, so anyway, so now I move to a different angle, which is the functorial approach to proof invariance. Okay, so I will speak about it maybe 10 minutes. And yes, so yes, so there is this famous Brewer-18-Kolmogorov interpretation of formulas and proofs, which say a proof of a formula A and B is a pair of a proof consisting phi of A and a proof psi of the formula B. Yeah. And then a proof, so this is easy, but something more maybe mysterious, okay, intriguing, is the fact that the proof of the formula A implies B should be an algorithm which transforms every proof of the formula A into a proof of the formula B. And then the question is, I mean, how do we express the notion of algorithm? And since, well, there could be algorithms formulated in different languages. And so one answer is the Lambda Calculus, and from an algebraic point of view, is the notion of Cartesian closed category. Okay, so which is just a Cartesian category, so with a product, which is closed, which means that there exists a functor here, so I write it as implication, with that property. So there is a natural bijection between the maps. So there are just as many maps from A times B to C as maps from here, B into A implies C. Okay, so and so there is a bijection between this. And now if we compute, I mean, if we look at the free Cartesian closed category, we see the Lambda calculus appearing. So the objects of the category are the formulas constructed with product and implication and a unit here. And of course, the objects of the original category C, which may be seen as the atom of the formulas. And then the morphisms. Okay, so these were the objects. The morphisms, they are the simply typed lambda terms, modulo here, beta eta conversion. And so the beta eta normal forms, they provide some kind of basis of the free CCC. And so if we look at it, you know, it's quite syntactic. Okay, it's the simply typed lambda calculus. And then there is here, so there are the basic constructions of the calculus. And we have the beta rule here, and eta expansion. Okay. And if we take all this, we construct the free Cartesian closed category. And what this means is that whenever I have a category here and an interpretation of the atoms in, so here it should be Cartesian closed. Okay, so when we are in this situation, then we can lift we can lift this functor that we had here. Okay, so this original functor, we can lift it to a functor here, which now transports every formula of the logic into an object of the category D, and every lambda term, every proof of the logic, into a morphism of this category. And so this gives a purely syntactic and type theoretic construction of the free Cartesian closed category. But something fascinating is that, in fact, the same kind of ideas are developed in topology to analyze the knot invariance. And so the difference is that instead of working with a Cartesian closed category, people work with the notion of ribbon category. Okay, so this is very, so this notion, in fact, originally comes from representation theory and quantum groups. Okay, so, and in fact, it's the same story that you want to construct invariants. So this is this functor which you can think of as producing invariance for a notion of equality here. And so in the previous picture, oops, sorry, this was like beta eta equivalence, or maybe, yes, let's say beta eta conversion. And here, and so we are interested in, if you like, lambda terms or proofs up to beta eta conversion. And here we are interested in, let's say, tangle diagrams, okay, but up to deformation, topological deformation. But the story is the same. And so, in fact, it's possible to think of game semantics as some kind of topology of proofs, okay? And so, okay, I was just discussing here the connection with knots, but I want to stress that because I really like it. So it's possible to think of a strategy. So here, so this is a strategy, but seen of game semantics, seen as some kind of as a topological entity. Yes. And in fact, in that, you know, if you look at this from that topological point of view, what happens is that negation here. So negation is like a move of a game. Okay, and a strategy. So I will show you a little strategy that proves that double negation of A, tensor double negation of B implies double negation of A tensor B. So if you look at a basic proof of that fact, okay, you can reduce the proof to just an ordering on the negation. And the ordering is here. It's 1 here. This is this. And then, and this is played by opponent. So each move is opponent or player. And here it's played by opponent. And then if you follow the negation in the proof or in the strategy here, you will get here the reaction by player, which is here. So this is 2, and this is here player. And then opponent reacts here with a move, and then the, okay, you follow the negation again in the proof, and you get here, which corresponds to move 3, and here move 4, again by player, whereas here it was by opponent. And so you see that a proof in the end is just describing the flow of negations. And so here we are 5 here. So in fact, so this is here. So this is the move number 5. and then we follow here, and we get here 6. So 6. So this ordering is extremely important of negations. In fact, it has to do with the theory of effects. So this ordering of negations describe the proof. And in fact, this ordering can be seen as some kind of as a strategy. Okay, so why a strategy? Because the idea is that, okay, opponent plays that move, and then player will play that move. And then opponent reacts with that move, and then player will play with that move, and then opponent plays that move, number 5, and then player will react with that move. So it can really be, you can really think of interactive strategies, in fact, as some kind of very topological in nature. But I won't speak about that now. I want to go to template games. I see we are a bit short in time, but I want to focus in the next 15 minutes on these template games and explain you how, how we can take this. Okay, you see, remember these intuitions about games and organize them in a language which is which is completely categorical. Okay, and this is really the what I will do now. Okay, so we're here. Yes. So I explain you game semantics, the basic ideas, the basic principles. But now I want to show you a concrete model. And the important thing about this concrete model is that it's completely categorical. Okay. So and this model explains in what sense the player and the opponent are synchronized during their interaction. And so there is this idea of space and time coming again. And so to that, I will speak about, I will use this very simple idea that we should have a category of polarities. And so this is, it's a very simple, stupid category. It has 2 objects, minus and plus, and 2 arrows, O and P. Of course, here this is a graph, and so I consider the category freely generated by this graph. And so this category, we will see, plays a fundamental role in the talk. And so really the idea is that a game, okay, and so this will be my definition, a game, so a template game, will be defined as a category, okay, just a category, equipped with a functor into the category I've just shown you. Okay, and the idea comes from coloring in graph theory. If you want to color a graph, so you have a graph and you want to color it, well, you will map it into a small graph whose nodes are the colors. So here it's the same. We have a category, and we will color it. We will label it, okay, by mapping it using a functor. Here it's a functor into that category of colors. So, and the colors here are just polarities, telling us, okay, here it's a negative polarity. So it's a polarity where it's player's turn. And here, this is the polarity where this is opponent's turn. And so because it's player and opponent's, player's turn on the left, minus, because the player wants to go back to the positive. And opponent wants to go back, to go back to the negative. And so opponents tries to move to negative, and player tries to move to positive. And so this gives really it's a way to label the original category A. And just for terminology, So the objects of the category A, often I will call them positions, and the morphisms, I will call them trajectories, okay? And well, I like to think of the category A as an unlabeled transition system, and the labeling is provided by the functor lambda. And so the polarity functor, which is a labeling functor, assigns a polarity plus or minus to every position of the game. And so I will say that a position is player when the polarity is positive, which means player is happy on that position, and opponent when the polarity is negative. And so an opponent move is defined as a trajectory, a morphism of the game A, which is transported by the functor lambda to that edge O, okay? In the template game, so sorry, the template category is so I use that terminology, is the very small category that I introduced 5 minutes ago, okay? So again, the category is really, it's very stupid, it's like this, and so this is opponent and player here, yes. And so every morphism of the category A, which is mapped on to that edge, is called an opponent move, and similarly, a player move is just a map, a trajectory in the game A, in the category A, transported to that edge. Okay, and so you can think really of a game as some kind of category. I mean, it's exactly a category where some edges are opponent and some morphisms are opponent or player move. And why? Because we have this functor A, which maps to this category. And so it's a very strong hypothesis on the category A that there exists such a functor into this very small category. It really structures the category A. And so we also have silent trajectories, which are mapped to an identity in the template category here. Do you have any question? No, it's okay. So I carry on. So now we have defined a template for games, which is this very simple category I've shown you. But now I will define a template of strategies. And so this is the template of strategies. Again, it's a very small, category, very simple. It's just the category freely generated by this graph. And so it has 3 objects, and all the maps are just sequences of these edges, their path in the graph. And so let's see how so this is the category which I will call a template of strategies. And let's see how we should think about these 4, okay, we have 4 edges here. And so let me explain what they mean. So we should think of OS and PS as the opponent and player move played at the source game, okay? Whereas OT and PT are opponent and player move played at the target game. Okay, and so we are interested in strategies playing between 2 games A and B. And so one way to represent the generators of the category is in this way. Okay, so here you see PS, OS, PT, OT. Okay, and so you see, for instance, OT here is going from plus plus to plus minus, and so here indeed in the picture we see that here OT is going from plus plus here, okay, which I represent in blue, to plus minus, where the minus part is in red, okay. And so if we look at a typical sequence OT, PS, OS, PT, so this sequence here, OTPS, or maybe I could draw like this, yes. So really this path here. Okay, that's the way it's represented in this diagrammatic representation. So the idea is that we have first OT, which intuitively takes a move here and plays it here. Maybe I will, yes. And then PS, which transports that move on the left. And so OT can be seen as an opponent move played on the target, whereas PS is a player move played on the source. And here, then OS is an opponent move played on the source, and PT is a player move played on the target. Okay, so that's the idea of this these edges. So each of the 4 edges describes an opponent or a player move played either in A or in B. Okay, either in the source or in the target.
What led you to choose those specific shapes, and so you put them on the different corners and things like that? Like what informed you to choose that specific arrangement?
Yes. So what I'm showing you is a reconstruction of game semantics in the language of internal categories. Yes. So we will see very soon that, okay, what I'm doing now is just showing you how to give a shape to categories. Categories which describe games, categories which describe strategies, in such a way that we can compose strategies. So I will show you in a minute, okay? But really, this choice here, okay, is some kind of is coming from the. It's really some kind of reflection of like traditional game semantics. Okay, so but we will see that this is the origin, but at some point we will see a property that will show that there is something deeper in a way. Okay, but just 5 minutes. Yes. So this is the. But again, yes, and so this category here, in fact, comes equipped with a span of functors. So we have 2 functors here. Okay, so this is the template of strategies and then the template of games here, which project on the source or the target. Okay, so if you look at, for instance, this picture that I was showing you, okay, the source functor will just project on, so it will project this sequence here on this part, if you like. This is the source, whereas the target will project on that part. And by this, I mean that typically PSOS will be mapped into OP here, whereas here the OT and PT will be mapped to O and P. And so it's really about, you know, I mean, the intuition is that these edges are describing a strategy between 2 games, whereas here, this is the strategy seen from the point of view of A, and here, seen from the point of view of B. And the idea of playing, you know, a strategy between 2 games is something important in game semantics that I will explain soon. Okay. So the second idea is that now a strategy between 2 games, okay, so will be defined as a span of functors here, together with a scheduling functor. And so here, this is the usual span, let's say, of functors or whatever. Okay, so it could be a span in a given category with finite limits, but here it's the novelty. Okay, that we have some kind of scheduling functor that describes how the strategies will play on A and B. Okay, I will show you. And the important thing is this diagram, which says that, okay, if I'm given, so S is called the support of the strategy. And now, if I take the support and I look at the span here, so which projects, so really the idea is that S, position in S, an object of S, will be mapped into a position of A and a position of B, and then the trajectory of S will be mapped into a trajectory of A and B. These trajectories, of course, are trajectories in a game A and in a game B. And so these trajectories, typically, they will be alternating between opponent and player. And so this extra information here tells us how the strategy will interleave, typically, interleave the trajectories in A and B. Okay, so if you go back to the, okay, maybe I will explain with here an example. So a typical scheduling BAAB. Okay, so I have my strategy here, and then I have my game A and my game B. And what the strategy does is, okay, opponent is playing here, and the strategy will just take that and play here. This is the player, proponent. And then opponent is playing here, and then proponent is reacting here. And so you see here that there is some information here about interleaving. So maybe this is where we have some time here. So this is 1, 2, 3, 4. Okay, and if we project on A and B, we don't have this information about the order in which the moves happen on each side. And so it's this extra information, in fact, is handled by this trajectory. Okay, so remember, this is a trajectory in strat. Okay, so it's really about scheduling the moves in A and B. Okay, so now, okay, once we have defined strategies like this, it's not, I mean, it's kind of obvious to define. So this is the notion of strategy between two games. It's very easy to define a notion of morphism between strategies, and I will call that a simulation. So it's just a functor between the support, making these three diagrams commute. Okay, if you think about it, it's kind of obvious. So you have here S, so you have a span here, B, so you want a theta here, such that this commutes, but moreover, not just that, also the information here about the scheduling, which is here. Okay, I mean, that's, so it's really, again, so this is really like what would happen in the category of spans. Okay, we can compare spans over two objects A and B, but this is really new. Okay, I mean, or a bit, yeah, a bit. I mean, and this is motivated by game semantics, and so we get in that way a category which I will call games of AB, with strategies as objects and simulations as morphisms. Okay, and now here comes really game semantics. We want to deduce from that a bicategory games, and by this I mean that we want to take strategies between two games and compose them. So typically we want to take a strategy between two games A and B, a strategy between two games B and C and turn them into a strategy between the games A and C. So we want to compose them, okay? And the idea is that, maybe we should think of composition of spans and try to use composition of spans to compose strategies. And so, okay, that's the situation. We have here, we have the first strategy. So remember the strategy, we have S, and here, this is the strategy sigma. Okay, so it's the support and 3 maps like this, making this diagram commute. Okay, and similarly for tau. Okay, we have these 3 maps here, which are functors between categories here. And the question is, how shall we compose sigma here and tau? Well, the intuition is that we want to construct a span here. Okay, I mean, this is really the very basic idea. We want to construct with a pullback something which like this, and then from this deduce the composition. And this is what will happen, but really something really important happens here, which is that we can do what I've just said at the level of the templates. So at that level. If we do that, if we compute the pullback here, so we are here and we compute the pullback here, we get something very interesting and very important in game semantics. So although people didn't realize it was a pullback, but it's something which is called a template of interactions. And you see, I've just defined it as a pullback. And the beauty is that, in fact, this pullback is extremely simple to describe. It's this category here. So it's the free category generated by this graph. Okay. And if you look at it, the objects of this graph are triples. And the triples describe the internal polarities during an interaction between 2 strategies. Okay, so that's why this is called a template of interactions. And so this is the pictorial way that I like to represent them. So each of these 6 here edges can be represented as a, here can be represented as a picture like this. And so the intuition is that we have a strategy sigma, the strategy tau interacting, and then we have different possible polarities. And this has to do with the way the strategies interact together. Okay? So typically some information comes here, okay, and will be transmitted here. And then, okay, we will see. So a typical sequence of such edges is C, B, A, B, C here. So you have some information which comes here and that crosses here, okay, and then goes here, okay. And this is this situation, and so this is sigma and tau here. And so in particular here, you have a point of synchronization where when tau tells something to sigma and sigma gets the information. Similarly here, you have another point of synchronization between sigma and tau. And this is what we want to represent categorically, and you will see it's something very, very nice here, because in fact, the reason why we get this category is the following one. So we can look at the category here of interactions and its 2 projections. So, okay, so really this category, we see the subcategory of the template of strategies times the template of strategies. And this, if we think about it, looks like this. So it's a situation where the 2 strategies, sigma and tau, are completely independent. Okay, so here in that direction here, I have sigma, and here in that direction I have tau. And so you have two strategies which play any kind of move, and they don't care about the other one. But when you want to synchronize them, which is the purpose of the pullback, what happens is that you get only a very limited portion of this square. And the reason is that, okay, if you look at it, what happens is that here, if you want to synchronize sigma and tau, you will have a first move and then a second move, here, 2, for tau, but which is also a second move for sigma. So you see here, the synchronization here is what we see here. So this is 1, 2, and 3 here is what we see here. 1, 2, here, synchronization, and then 3. And so, oops, sorry, there is this nice synchronization between sigma and tau, which we see appearing here in this diagonal. Okay, and what I'm doing is very much inspired by algebraic topology. I'm trying to understand how strategies and game semantics is in fact related to algebraic topology. And here we see the diagonal, which is really the synchronization between the strategies, synchronization between sigma and tau. Yes. Okay. And if you remember, Abelard, Eloise, at some point, if I tell you something, you are listening to me at the same time, hopefully, and conversely. And this is this point of synchronization on which logic is based. And so, oops, yes. And in fact, when I draw this picture, you should think of it really as this graph here. So when I write this, it goes in two directions. It's opponent here and player here. Okay. So we see, I mean, what I draw here. Okay, if we look at it in this way, I mean, we recover this graph here. Okay. And so really, what I'm doing is I'm explaining how to synchronize games and strategies. And I will go a bit fast because I think, I don't know exactly what are the time limits, but if you give me 10 more minutes, I think I can maybe. But I don't know whether.
Yeah, I think that's fine. There's,
if nobody stops me, I will carry on for 10 minutes. Yes, is it okay?
Yeah, I think that's totally fine. If people need to go, they can drop out.
And if someone stops me, okay, I carry on then. Okay. So, okay, that's nice. I've shown you how the pullback of two things, I mean, it represents synchronization between the strategy sigma and the strategy tau. But now there is something really important, okay, and extremely nice and reassuring, is that, in fact, we will see what I'm constructing is an internal category, okay. So the templates I'm manipulating, in fact, game, and then we saw I have strat, and then I have here int, which is the interaction. Okay, in fact, they may be seen as just the hierarchy here. So this is here and 1 and okay. So the beginning of a hierarchy, which is this hierarchy of the objects and the morphisms and composable morphisms and so on of an internal category. And this is extremely important and reassuring. And what I claim is that this is really the secret, in a way. I mean, the reason why game semantics exists and works. Okay, so I will describe the structure of this internal category now. So we have hide here, which is a functor from the template of interactions to the template of strategies. And what it does is very, okay, this is the formal description here. Okay, but really the idea is that it hides the internal state here. Okay, and so pictorially, which is the way I prefer, what you have here is that you have, this is the interactions. okay, between, remember, sigma and tau, okay, really, two strategies. So this is sigma and this is tau. And here is the composite, if you like. So, I mean, that's the intuition, the composite of sigma and tau. And I will justify what I'm saying now, okay? So the idea is that you don't want to see what's going on inside the interaction between sigma and tau. You just want to look at it from the outside. And in fact, what I'm saying can be formulated algebraically in a neat way. So the idea is that we will take this pullback I was showing you before. So in particular, we have this here. And this will be the support of the composite. So this is the support of sigma composed composed with tau. And this support comes with a functor into strat, because it's a strategy, so there should be a functor from the support, which is just the functor that we get canonically into the template of int. And this functor comes from the fact that the template of int is a pullback here. So pullback. So here we have the two functors which describe the template of int as a pullback. So this functor is canonical, is the solution of a universal definition of the template of int. And then we use this extra functor that we I've just shown you, which is the hiding functor. Okay, and so this is composition. And so this shows that composition of strategies, okay, is just synchronization, which is pullback. Okay, so we can think of the pullback here. Oops, sorry, the pullback here as really a synchronization plus hiding, and the hiding is hiding, what happened between sigma and tau. Okay, good. Okay, so this is really the hide functor. Now, what about identities? And so there is something absolutely wonderful, which is that there exists a functor, copycat, which goes from the template of game to the template of strategies. And it does something which in computer science was never really considered. What it does is it will duplicate the positions of the polarity category. So what this means is that minus will be mapped into minus minus, and plus will be mapped into plus plus. And what is even more remarkable is that here, the edge O will be mapped to a path OTPS, and P into a path, okay, OSPT. And what is important here is that they are paths, they are not edges. Okay, so we see here why we really need categories. What I'm doing here would not work with transition systems, okay, which is very unexpected in a way from the point of view of the history of game semantics. And so how does it work? Well, this edge here is mapped to this sequence OP, okay? And this edge here is mapped to this sequence OP. And here, okay, you see the copycat strategy that I described earlier. The copycat strategy which enables you to win against Karpov and Korchnoi, okay, just by repeating the moves. So the point is that every move of the original game, okay, should be turned into two moves. Okay, so opponent playing the move, and then player reacting to the move. Okay, and so the copycat strategy is just defined as this span together with this functor, which, remember, has to go. So A is the support here. So this is the support of the strategy. and it has to go to the template of strategies. Okay, so it does in 2 steps. First, we use the here the polarity functor into the template of game, and then this new functor here, which I've just introduced. And so this is the identity strategy.
You know, we only
So
get
you
half
see,
an hour.
what I'm doing here is I'm using structure on these categories: game, strat, and int, to correlate the usual definitions of composition and identity in category of spans. Here, spans of functors, and what I have in mind as a category of games and strategies. And so this is the key observation, is that the 3 categories I've shown you, so this one, and this one, in fact, the reason why they make everything work and why game semantics works so nicely is that they define an internal category in cat, okay? Which means, I mean, another way to think of it is like it's a double category, in fact. And so the picture I was showing you, you can think of them as pictures of pictures of a double category. And so, and hide here and copycat are the composition and identity of the internal category. And as an immediate consequence, if you work a little bit, you can show that games, okay, is a bicategory. Okay, so we have a good composition and we have a good notion of identity. In the same way, we can show that games is symmetric monoidal, and in fact that it's star autonomous, which means it's a model of linear logic. Okay, so and by model of linear logic here, I mean of the tensor and the cotensor or the par, and in fact there is also here, I mean, an interpretation of the plus and the with. Okay, and the incredible thing is that all these results are based on the same recipe. So let's look for the tensor product. So the idea is that we need to construct an internal category, another internal category. So for the moment, we have one internal category, but we construct another one with 2 internal functors. Okay, so it looks like very formal, but in fact, it's very cute and combinatorial. Okay, with this structure, we will have enough to show that we have a tensor product on our bicategory. And so let me just speak a little bit about pick and pins. Okay, so pick, yes. So yes. So let me go here. Yes. So this category here for the tensor product, what it does is it describes the rules of the game for a tensor product. So you remember, for instance, we know that opponent can switch game, but not player. Okay, proponent is not allowed to switch. Can switch between games, and this is in fact what is described here. So, so this says, okay, I have, I'm in a situation where the 2 games here, opponent can move, play that component here, and then player will go back, or that component and player will go back. But whenever opponent has played, okay, so imagine, for instance, opponent has decided to play the this component. So opponent plays here, then player has to play on the same component. So what I'm describing here is really the scheduling rules of the tensor. And the nice thing is that, in fact, the 3 positions that I describe are the possible positions in a tensor product. So when you have A tensor B, okay, if you take a state of A tensor B, it can only be of these polarities. Okay, so for instance, if you take a state X tensor Y of A tensor B, it has to be either minus and plus here, so X is of polarity minus and Y is of polarity plus, or both of them are plus, or yes. So what I'm describing is really all the possible polarities in a tensor product. And then the point is that we can also define a template of strategies for this tensor product, and then show that it defines an internal category. Okay, and then build these two internal functors. Okay, and doing that is a lot of fun because it's very combinatorial. The categories are very small, and so I just want to show you pick and pins, how they work. So this is just the Cartesian product of this category. You remember? So this is the very simple category like this, where we have yes, maybe, I mean, remember. So this is based on this category here, where we have opponent and player here, and this is plus and this is minus here. Very simple category. So, but when we take the Cartesian product, this is what it looks like. And what this category does is picking the polarities which are allowed by the game semantics. So minus, tensor minus is not allowed. So we should remove it. And this is why I call this functor pick. It picks the good polarities. It picks the situation which are polite, which are from a logical point of view, which are allowed from a logical point of view. And so here, this is pick, but at level 1, in the same way as we had pick at level 0, it's an internal functor. Pins is doing something different. So it's looking at this tensor product and then decides what polarity. So typically, for instance, X plus tensor Y is considered as a position of polarity positive. Okay, and so plus plus here is mapped to plus, whereas minus plus and plus minus are mapped to minus. And this is also an internal functor, and this is where I wanted to, the point I wanted to reach. So this is the way the tensor product of two template games is defined. We see it's very simple. So we have a first template game and a second template game. So the first thing we do is we take the Cartesian product here. Okay, and this A times B, okay, can be seen as just the two games A and B put together with no synchronization, no between them. But then pick, the functor pick here, will pick the states, the positions in A times B, which are valid from the point of view of the tensor product. And so with a pullback in cat, we will get the game A tensor B, which is a category, but a category with a functor here into that template here. But then we use pins, okay, here, to obtain this functor, which is just the composite of these two functors, into that here. Remember, this is the template of games, okay? And so we have defined a new game. And so if you remember, I mean, the way we had the two boards here, and we wanted to define a tensor of two boards, this is the way it's done here in template games. Okay, so it's just the Cartesian product of the two boards. So I start like this. So no synchronization involved. But then using the templates, I'm able, and using these two functors here, internal functors, pick and pins, I'm able to synchronize the two games A and B. And really, I like to think of it as a categorical version of Milner's idea of synchronization algebra, which was very important in the 80s in process calculi. So process calculi and concurrency theory. And so what is nice here is that we can import ideas coming from computer science into category theory in a very natural way. I mean, it's not that. This import also shows the true nature of game semantics, I believe. Yes. Anyway, so I just want to show that you can do the same for the co-tensor. It's exactly the same constructions, except that opponent and player are reversed. And so it's exactly the same thing. And in particular, if you want to define the co-tensor, you use a pullback along the peak and pins functor, but for this template of co-tensors. Okay. And then you get something quite nice, is that, in fact, in linear logic, there is this famous distributivity law. And it's possible to analyze it in that language. And so really, the linear distributivity becomes some kind of synchronization, I could say synchronization principle, so synchronization policy or synchronization structure. And it's the first time, in fact, that linear distributivity can be expressed in that way. Because, in fact, this is the first game semantics. I will explain that in a few minutes, but very briefly. But it's the first game semantics of the whole of linear logic. It's something which is important, and maybe I should note that. Okay, so our games, so template games, do not have an initial position. Okay, so, and this is the reason why the model, so this is a model of linear logic of non-polarized. Okay, I'm getting a little bit technical here. I'm sorry, but it's the first model of non-polarized linear logic as a whole. Yes. Anyway, so linear distributivity can be analyzed in that way. And I will just go very, very fast on the exponential modality. Just say that in order to interpret, so remember, it's about interpreting bang of A. So, and the idea of a repetition of a game with a tensor product. Okay, and so here, what I will use is the fact that sim, which is the free, the functor, which associates to every small category, the freely generated symmetric monoidal category sim of C. Okay, this is a Cartesian monad. And so, in particular, by Cartesian, it means it behaves properly with respect, or nicely, I should say, more than properly, behaves very nicely with respect to pullbacks. And from that, we can deduce the fact that it will transport any internal category into an internal category. So in particular, if we take the internal category of polarities, it will transport it into an internal category, which we can see as a new template. Okay, so if we start, so what I call a template here, it will be an internal category. And so this is a new internal category. But then the objects of sim of, remember, so again, this is a template of games. And so sim of the template of games, the objects are just finite words on the two letters plus and minus. Okay, because this category has two objects, plus and minus. So the objects here are just sequences plus, minus, minus, plus, plus, minus. So they are the objects of this category. And what we will do is just restrict. So we will consider the subcategory, the full subcategory, whose objects are exactly of that form or of that form. So either only positive polarities or exactly one negative polarity. And this reflects the fact that in the exponential game, the opponent can only open one copy after the other. So that was a question that I think you asked me about maybe 1 hour ago. Yes. So opponent can only open a copy after a copy, and not two copies at the same time, or three copies. And so that's why we only have a minus here. And so just using that, we can, deduce a template for the exponential, which is just obtained by restricting theme of the template to that subcategory. Okay, and this can be done in a very neat way categorically. Okay, and then we have, again, two functors pick and pinch here that will enable us to define a bang of A by a pullback here, okay, which defines this map, followed by composition. And so the game bang of A, the template game bang of A, is defined just by a pullback plus composition. And by the way, this is really some kind of bifibrational property. This is a pull, and this is a push here. Okay, so it's really defined by pull and push. Anyway, an interesting phenomenon is that the so-called silly isomorphism, silly isomorphisms, okay, that are famous in linear logic that I mentioned earlier. In fact, they are interpreted here up to up to homotopy. So it's not anymore an isomorphism. It's not even an equivalence. Something a bit more subtle, which requires to consider the model structure on cat. Okay, so I'm happy to discuss about that with anyone interested on the connection between games and homotopy theory. But the nice thing is that in that way we get games as a model of linear logic, including the bank, this exponential modality, if we work up to homotopy. And so I'm finished now. I just want to say that we could use other templates where opponent and player would not need to play one after the other. So a situation where opponent can play several moves in a row, and then player several moves in a row. And the idea is that instead of playing with the original template that I called game, we just play with another template where opponent can, for instance, so the template is here. Maybe it's sorry, the template is here. Okay, it's just one polarity and then opponent player here. And so is the category freely generated by this graph with the equality that OP is the same as PO. Okay, just to say that the order in which opponent and player played really doesn't matter. Okay, and then we get again an internal category, and we can, what I did for the original template of sequential alternating games, I can do exactly in the same way for that template. And so that shows that we can have different templates and different way to structure the logical interaction in space and in time. And what matters is that we have internal categories with monoidal structures and so on. Okay, so I'm finished. So conclusions. So here we have a notion of games played on categories, and something which is interesting from the point of view of game semantics is that the copycats are synchronous. Okay, so we play, so if you like the strategies, they play opponent player moves synchronously. There is no, so typically if opponent plays and I answer as player, it's one move, or rather one move, but which cannot be decomposed in opponent player. It's one action. Okay, it's synchronous. The opponent and the player are playing at the same time, if you like. And categorically, it means that here we consider the path as really some kind of atom, okay, in the strategy. So the strategy doesn't play moves, maybe it's the best way to say it, but path, or something that I call opponent player moves, OP moves, yes? Okay, then of course it provides a very nice recipe to construct new game semantics. And here in my original paper, I considered three templates. So the alternating one, which I've shown you, then the concurrent one, and then the span, which is just the trivial template. So where the strategies are just defined as spans, okay? And so all these categories can be seen as categories of labeled spans or games. Okay, and then we can get a model of differential linear logic using homotopy theory. So something I really like is that the model I've shown you can be also used in some way to interpret concurrent separation logic. Okay, but interestingly here, I use co-spans instead of spans. And this is work I've developed with Leo Stefanesco, who's finishing his PhD currently in Paris. And there is a nice asynchronous sortness theorem. So if you're interested in concurrent separation logic, maybe have a look at our 2 papers, or 3 papers on the topic, yes. And currently, we are trying to extend it to higher order concurrent separation logic, which is a nice perspective, I think. And then, okay, something I'm very keen on is to interpret games not just as categories, but as 2 categories, and in fact, as higher categories at some point, instead of just categories. So it's very important when you play games to know that 2 different trajectories are related by 2 cells, okay? And it's important and interesting to analyze this phenomena. And then the fact that I use, so you know I speak about tensor product. Okay, so this is really about linear logic. But at the same time, the language, so all this is kind of embedded into a category with finite limits. So it's a category cat here, but it could be another category with finite limits. And so that means that it's a way to do linear logic and games in a language which is very reminiscent of dependent types. And in fact, the connection with homotopy theory that I mentioned is really influenced by homotopy type theory. And so I think it's interesting to try to connect dependent types with linear logic. I'm not the only one to think that, but here it could be an approach, and also monadic stacks of effects and co-effects. There should be some kind of combined theory, and I'm thinking a lot about it, but so I have elements, but not the full picture yet. And another point is the games I consider, they don't have an initial position. And if they had an initial position, this initial position should be an opponent or a player initial position. And so the template games would be polarized, either opponent or player. And so the logic also would be polarized. And so really it would go to something I like to call tensorial logic rather than linear logic. And also I spent time thinking about that. Okay, I think I really used a lot of my time and more. The good thing is that, you know, I don't force anyone to be here, so you can leave, you can have a cup of tea or whatever and let me speak. But I'm happy to take your questions now if you. So here are a selection of a few papers that I find interesting and relevant to that talk. So yes, that's it.
Thank you very much. Yeah, I think it's totally fine going over. I mean, that's what's great about the internet, is that we can always choose to walk away very easily. So
do you have any questions?
Okay, I have First, a request. Could you forward a couple of your papers that are most relevant to the talk and the slides also?
Yes, I will.
Okay. Then I had a question. So if we go back to the slide about the product of the strategies, the free product, they're basically completely unsynchronized. And then the pullback basically is forcing synchronization, presumably by essentially removing some of the transitions that are possible.
Yes, exactly. So the idea is that, you know, sometimes I like to think like in physics. So you have two systems, which are the strategies, and they're independent. And then the question is, how do you force them to interact together?
Yeah.
You know, I mean, you know, an option in life is like exactly what happened about 20 minutes ago. You know, I asked you for a sign, I didn't get the sign. So in that sense, you know, I was like a free particle. Nobody would. And so here, if we look at the picture, yes. So let's yes. And that's why I say, you know, it's logic. I mean, I think logic is about meaning, but it's also about the choreography. Yes, the fact that, for instance, you will speak, I will stop, and okay, and so you will, and so this is what I try to understand with these little pictures. So okay, yes. So here. Yes, so this is, I think, the picture you wanted to discuss, maybe, yes? So, okay, but of course, it works at two levels. So, okay, I go here. So I erase now, yes? And we discuss again. So I think this was the slide you wanted to discuss.
Right, yeah, yes.
Yes, so you see, what is interesting is that it's really about trying to make ideas from, let's say, computer science, okay, and logic, into these pullbacks, okay, trying to. So, so here, when we do that, okay, so we should think, okay, what I call templates, we should think of them as labeling. Okay, so what this is saying, okay, is that we have two systems, A and B, which are independent. So because it's just a Cartesian product. Then, so in particular, it looks like this one. Okay, it looks like, okay, I will show you the category is really like plus, or maybe just to make it, it's because it's in fact drawn here. Yes, so this is the oops. So this is the category that we have. So, you know, so this Cartesian product is really this here.
Yeah.
And so it says, okay, in particular, I could imagine here, so I have plus, typical situation is I have then plus minus. And so here it means that it's plus with opponent playing. Yes. So opponent moved, and okay, from really they are pairs. Yes. And then here, minus minus is opponent again playing minus. This is forbidden by game semantics because opponent played twice.
Right.
And so, so this sequence is forbidden. And so how do I describe the fact that it's forbidden? I say, okay, I should pick the positions which are accepted. And so this is what this does here. So these are all the positions which are accepted. And if you look at it, this is really, okay, I wrote it like this, but it's really like this. It's opponent plays on the right, and then player reacts on the right, because player should always play on the same component. Player is not allowed to shift. or opponent prefers to play on the left component, and then player answers on the left component. These are the only acceptable sequences. So they are the, they are the kind of secret rules of the game, I mean, in the sense of, they are, and so that is, okay, I represent that way because, in fact, when I, with one edge, I represent these two edges, yes, OP. And maybe just to show you the co-tensor, sorry. The co-tensor is just the opposite. It picks the other position. I mean.
Okay, now suppose I wish to, so this model is basically the alternation rule in games.
Yeah. And so, by the way, I should say that now, in order to define A tensor B, what you do is a pullback, which means you pick. I mean, this is what you were saying, I think. I just.
Yeah. Okay, so suppose I wish to model some kind of, I don't know, reactive specification. Okay, so the proponent produces a sequence of bits, and the opponent must compute some partial function on the prefixes of the bits. Okay. How would you do that? And how would you define which of those functions are realizable and which are not?
Mm-hmm.
For example, functions that depend on future inputs would obviously be not realizable.
Mm-hmm. Mm-hmm. Yes. So here, yes, I understand. So here, okay, so I use a very strict notion of alternation. But with this notion of alternation, I could implement a list. For instance, you mentioned a list of, so I could imagine, for instance, interactively, you give me a first element of a stream, and then I say, okay, maybe I want a second one, yes? And then you give me the second one. Then I want the third one, and then you give me the third one. And then, okay, that's enough. I can give the output. Yes.
Right. Okay.
So I mean, that would be it's half of the answer. Okay, but that would be an alternating implementation of something like transductors.
Yeah. Right. Yes. Exactly.
And so I could represent transductors, by the way, in this language.
Okay.
So the idea is that I don't take polarities. Okay. I just have a notion of move like this. So it would be like, let's say, some kind of like letter or atom. I have this template here. It's just saying, okay, every word is a sequence of letters. So I would have like A star, for instance, the finite words on an alphabet mapped into this. And, okay, so just counting. So this is like, so like it's just, or maybe this is a bit. This is just natural numbers. Yeah. This.
Okay.
I mean, the category freely generated by this category is just the category is one object and the natural numbers as morphisms. I mean, okay. What I'm saying is just take, the free category generated by letters, and this map, okay, like this. That, and then, okay, just to show you how to build a category of transductors. Then the notion of strategy here would be, I mean, this encore of strat would just say, okay, I take a letter here and I should map to a letter on the other side. And then I take another letter here and I should map to another letter here. So, okay, what I'm saying is this format that I'm describing can, in fact, describe different modes of interaction. So in particular, transductors, which are from the input to the output. So if you want to do what you were telling me, yes, to have a finite list, for instance, of letters that produce a letter, and not just one letter producing a letter. This is what you were suggesting.
Right, yeah. Well, let's just to take a concrete example. So suppose every time the proponent plays, he sends a letter A, sort of think of it as a clock tick, okay?
Yes.
And the opponent is required, when the number of clock ticks received in the past is composite, you output a 0, and when the number received is a prime, you output a 1.
Yes. Mm-hmm.
Okay, as a sort of very simple.
Very good. Yeah. Yeah. So yeah. So the point is, we want to describe computational situations which can be composed.
Yeah.
Yes. And so, for instance, this function that you're describing, we want to compose it with another function.
Right.
Okay. And so maybe we want typically to define functions from streams to streams, or from finite list to finite list.
Yeah.
Something like transducers, but maybe a bit more general, that can take a number of elements. And yes. Right. And I'm saying this can be accommodated. So, as my claim, okay, and we can discuss that offline. I'm happy to explain. Yeah. So my claim is that, in fact, in the 80s, people thought a lot about how to compose processes.
Right. Yes. Boatload of work.
Yes. So I mentioned synchronization algebras, and there were like various.
Yeah. Billion models doing it.
Yes. Yes. And the thing is, in order to compose, you need to have a notion of labeling, which can be, for instance, for CCS, it will be the letters and so on.
Right.
And then they were able at the time to understand that composition was produced by pushing and pulling, like this kind of pullbacks and composition of labeling.
Yeah.
And it is what is replayed here, but on categories. So it's it's just one dimension up, but it's fundamentally the same kind of ideas. And so transducers, for instance, usually they are letter to letter, but for instance, if you want to have several letters, you can imagine to have a modality. So, like, for instance, you have a transducer from A to B.
Yeah.
But then you want maybe to have a transducer, like I write bang A, but bang A would be, in fact, A star, okay? Where each letter is, in fact, a word.
Right.
Okay. And now, the fact that you have transducers from finite words to letters, the fact that composes, because that composes, yes, in fact, if you have a fact, you can. It has to do with properties. So here, this thing here is a comonad. Okay, so maybe it's a bit. Do you like that kind of concept? I mean, it's just something like this that says, okay, so I have a transducer. Okay, it's just convenient way to look at modalities. So you say, okay, I have a transducer, for instance, from A to B here, A star. Okay, so, and then another one from B star to C, and I want to get something from A star to C. Yes.
Right. Yeah.
And then, well, you can say, okay, from that I get something like, something like A star star into B star.
Right.
And then this kind of, yes. And
right.
So, I mean, what I mean is that it's possible to adapt and think in a kind of logical or modal way about these situations. And I'm trying to work not at the level of the objects themselves, but at the level of their labelings. I mean, that's one way to summarize what I'm saying. You know, I mean, and I think it's interesting to think not just about the computational situations, but about what I call here the templates. That means they're kind of structure, internal structure.
Right. Okay, I have a
well, maybe I think it's about time we wrap this up, since it's been 2 hours. So maybe Paul can email Paul.
Yeah, I think it's good if we have a little chat and discussion.
Yes. Yeah, we can. Let's arrange that for next week sometime. I have a bunch more questions, but send me your papers first. And
yes, please. I will do that, and I'm happy to interact with you. Yes.
To look through them, and then
very good. Maybe are there any other people who want to ask a question, and we do that, and then we're finished. No, but it's great. You know, I'm really interested in automata theory and transducers and all these things. So if you have intuitions and interest in that, I'm happy to share.
I have a particular idea that I'd like to discuss with you.
Okay, good. Very good. You know, I mean, you know, I'm at home. You're at home, probably. I don't know. Where are you currently?
Augusta.
Okay. Yeah. So.
Yeah. So yeah, plenty of time.
Yeah, and a good reason to stay at home.
Yeah.
Yeah. Okay, great.
Okay.
Well, thank you so much, Paul-André. It was a great talk. And
by the way, I didn't realize what is the usual format. I pushed it probably a little bit, but.
Oh, you mean time-wise, or?
Yes.
Usually it's around an hour.
Okay, so then.
But I mean, I figure online, that's when we're in person. So I mean, online, it's like people can come and go, and you know.
Yeah, exactly. I felt like, you know,
I feel like it's more open at that point, so I just let it run. It's totally fine.
Okay, yeah.
Yeah.
Very good. Great. So if there are questions, I'm happy to answer them, and otherwise, I'm also happy to answer by mail or whatever.
I had plenty of questions on the category theory Zulip chat.
Okay. So maybe we can, I mean, I can answer them now, or you can email me and we can do a little exchange.
Oh, yes? I think he was saying that they're on the category Zulu, the new Zulip chat thing. I'm not sure if you're on there or not.
Oh yeah, sure. I joined, yes, I joined the Zulip. Yeah, it's nice. It's interesting. Yeah. Okay.
Yeah.
So I will have a look then.
Cool.
Yeah, it was an interesting, you know, it's not, I mean, I think we need to adapt, and it's interesting. That means we meet other different people, yes?
Oh yeah, definitely. No, I think the
I'm
Zulip
grateful you
idea
invited
really
me.
Good one.
It was a nice thing, and
yeah.
I'm happy.
Yeah, I'm on there too. I think it was a good idea. I think sometimes the categories mailing list can be a bit limiting because they don't let you post certain things and stuff like that. Where Zulip would be more free to be able to have.
Zulip, yeah, it's nice. I looked at it already a little bit. Anyway, I think we're, you know, experimenting, and everything is new in a way. It's a new paradigm. I'm sure there are so many things that can be done, and we'll see what is the best adapted. I mean, what is, you know, best adapted to us. I think it's also important to keep focus, and so that's the whole challenge. Yes. So
yes.
To keep a focus at the same time to be able to have these tools, and you know, even without the current situation, we definitely need to do that.
Yeah.
Because we need to keep connections at the same time. We need to be, you know, carbon conscious.
Yep.
So it's I think it makes sense. Also, there is an element of freedom in these tools. You know, people can join. It's more.
Yeah. I agree.
Yeah. Anyway, we agree. So
we're all on target.
Yes, exactly. No,
okay, great. So I think we can probably wrap it up there. And thanks again.
Yes, thank you. And please don't hesitate to email me, ask me questions. I'm happy to interact. Yes.
Great. Sounds great.
Okay.
Awesome.
So,
well, we all abandoned, so off we go.
yeah, goodbye. Thank you.
Thank you.